What I'm drawing here is a cross-sectional area in any bar or any beam. The beam or the bar is a consistent shape, alright, and it's consistent all the way along its length. The N and the A denote the neutral axis, and the lines that are being drawn represent layers within the grain structure. If you were to snap the bar or the beam, or cut the bar and the beam, you will be able to see that each, in steel, plastics, any sort of structure, there is some form of grain running through it. At a molecular level, within the grain, there are layers. If you were to put the steel under a microscope, then this is what you would see. The layers run the length of the cross section and they're tightly packed. Now what I'm drawing is basically a simplified view of the above drawing. The reason for doing this is there's an awful lot of information to put on it. So you can see that I've drawn the bar again. I've redrawn the neutral axis. However, I've just picked one layer and then drawn and filled in one layer. The info that you need for this is the N and the A represent your neutral layer, or your neutral axis, sorry. You then have your layer. Alright, your layer has a length, which is in this case denoted as B. You then have a height of a layer, which in this case I've drawn as a derivative of y. The y is the distance from the neutral line down to the top of the layer. Now y can be anything, it's completely arbitrary. You can have it next to the neutral axis, you could have it further down, you could even have it right at or just below the edge of the. So what we have is we have a stress that is acting on the strip. Now this is represented by the formula sigma equals y, sigma equals Young's modulus times by y, which is the arbitrary distance, divided by the radius. You get the radius from the previous drawing that we did within the class. We then substitute, so we now have the differentiation of F, or the force, is equal to sigma, the derivative of A. We substitute, and if you remember like Ohm's law, bits and pieces, it's like a small triangle. So we've now got sigma is equal to Young's modulus times by y divided by the radius, which then is the derivative of force is equal to Young's modulus times y divided by the radius times the derivative of A, which is your cross-sectional area. So as our beam is made up of many layers, and to try and explain what is happening in real life, I've now drawn two more pictures. One is our cross-section, which we've seen before, and then the other one is basically a side view. And in the side view you can see that the bar is, or the beam is bending slightly because the mass that's being applied to it. So what is actually happening? Well, 50% of the layers are going into tension and 50% of the layers are going into compression. Therefore, we're trying to balance the forces. The total force acting on the section is the sum of all of the small forces. So therefore the force is equal to equilibrium, the derivative of force is equal to the equilibrium of Young's modulus, alright, times that arbitrary distance divided by the radius, the derivative of the cross section. Then what we have to do is integration. Now when we do the integration, we're integrating F, alright, or force. This is still sort of theoretical. So therefore force is equal to the integration, and your limit in the integration, we put a top and a bottom. Those top and the bottom would be the distances or the thickness of the entire bar from top to bottom of your layer rather. Then you have Young's modulus times by R times by Y divided by R times by the differentiation of the cross-sectional area. When you actually melt all this down, you end up with one formula, and the formula is the integration with the top and the bottom distances with the arbitrary distance of y times the differentiation of A, or the cross section. Now this is a definition, right, and it's a definition of the first moment of area of the shape which is around the centroid, or the exact center of the beam or the bar. And basically our answer is 0. So 0 is our first moment of area. So what has actually happened? As we've said in the previous drawing, in reality what we have is you have the cross section, you have your neutral axis, 50% of our layers are going into tension, 50% of the layers are going into compression. So our centroid, which is right in the center of mass of our object, or rather the centroid is the center of mass of our object, the centroid isn't going anywhere. It's not moving up, it's not moving down, it's just bang on in the center. So everything is in balance.